All right, on Friday, we were talking about scalar quantities, which have only magnitude, and the three scalar quantities we went over were speed, distance, and time, okay, or v, d, and t. Okay? And we talked about vector quantities, which have both magnitude and direction. And the two vector quantities we talked about were velocity and displacement. Right? We talked about them in the context of walking from your house to Walmart. Okay? And we said, you can't walk in a straight line, so there's a certain distance that you have to travel. That's a scalar measurement. It is how far you went to get from your house, your initial position, to Walmart, your final position. Okay? But in the end, in a straight line, your displacement is a much smaller length. Okay? But it also has a direction. Right? So those two trips from different points of view look a bit different. But it gets even crazier when you turn around and go back. Because if you go back along the same path, when you get back, you have traveled a distance of 8 kilometers. And if it took you an hour, you walked at 8 kilometers per hour. But when you get back to your house, what was your displacement? 0. Because your displacement measures your change in position. If your initial position is your house, and your final position is your house, then your position hasn't changed no matter what you did in the interim. You came back to where you started. So, yes, you've walked. Yes, time has gone by. But from a vector perspective, you have accomplished absolutely nothing because you have returned to the same point from which you began. Okay? Even though maybe you walked all the way around the world. Okay? So your distance is a really, really big number, but your displacement is still 0. Okay? Does that ring a bell for everybody from Friday? Okay? Because what we're going to do today is look a little bit more at the math of things. We're going to look at using v equals d over t, manipulating that, and dealing with both scalar and vector perspectives on simple two-part trips where you would only go forwards and backwards. Okay? So I'll give you an example. I'm going to put this spray bottle on the floor to mark my initial position. Okay? And then I'm going to walk east. Okay, that direction is east. I'm going to walk east 5 meters. It's an approximate measurement, but we're going to say that that's 5 meters. And then I'm going to walk west 2 meters. What's my distance traveled? 7 meters. I walked 7 meters. Okay, I went 5 meters, then I went 2 meters, I went 7 meters. But what's my displacement? 3 meters east. Yeah, it's a vector quantity, right? That's why I made a big deal out of pointing out that that way was east. Okay, my total displacement is 3 meters east. Okay, those are the kinds of things we have to keep in mind. Okay, again, it's looking at that trip from 2 different points of view. What did I do as opposed to where did I end up? Okay, that's kind of the difference between scalar and vector observations of the same trip. Now, in Science 10, that's as complex as it gets. Okay, nothing will ever have an angle. You're never going to have to do any trigonometry. Okay, it's going to be you go up and then you go down, or you go north and then you go south, or you go left and then you go right. It's never going to be anything other than forward and backward. Okay, now mathematically speaking, how do I represent east and west? Are they opposites? How do I represent opposites mathematically? It's a tricky one. Positive and negative. Yeah. Okay. So, and that'll follow you through. That'll follow right into physics 30. Okay. You break everything down to an x component and a y component. If I go forward on the x, that's positive. If I go backwards on the x, that's negative. Okay. If I go up on the y, that's positive. If I go down on the y, that's negative. Okay. And I just break everything down to this thing is the opposite of that thing. So one of them is positive and one of them is negative. And it'll never be more difficult than that. Okay. All right. So, that's the formula we talked about day before, right? Now, just so that we understand, this formula, okay, or actually these two formulas, so V equals d over t, so speed equals distance over time, and velocity equals displacement over time, actually also mean this, okay? They're not usually written this way, but they mean this. Average speed is total distance divided by total time. Okay? We've only ever dealt with like simple trips where it's like, there's my distance and there's my time, so they were automatically the totals. But when we start dealing with trips that have two parts, then we have to put the two parts together. Okay? It's the same for the vector version. Average velocity is the total displacement divided by the total time. Okay? It always means that, we just never write it. Now, is anyone thinking that's an odd way to calculate averages? Okay? Your whole life, you were taught you calculate averages by taking all of the numbers and adding them up and then dividing by the number of numbers, which is completely correct, provided that all the parts that you added together represent equal parts of the whole. So when I'm calculating a class average in here, each one of you represents an equal part of the class. So I can divide all of your total of all your scores by the number of you. Okay? Each one of your scores counts for an equal part. But let's say this happens. Let's say I go to Edmonton and I travel the first 300 kilometers at 110 kilometers per hour. And then the last 3 kilometers, there's construction, and I have to slow down to 50 kilometers per hour. Do I calculate my average speed by adding 110 plus 50 and dividing by 2? No way. My average speed is like 108, okay? Because most of the way there, I went 110. I have to weight the average, and that's what this does, and we'll see that when we get into some other kinds of questions. We always have to say, all right, which part of the trip is the biggest? And by adding the totals and dividing by the totals, you get a weighted average that represents the correct number. Okay, is everyone all right with that? All right, so there's nothing wrong with calculating averages the way you did it in that situation. Okay? But once the parts are not equal parts of the whole, then we have to do it differently. Okay, let's look at manipulating this formula. Should I use a triangle? Don't use a triangle. I will become enraged if I see a triangle anywhere on your papers. Okay? Because triangles are useless once you get to a formula that has more than 3 variables. Unless it's a special formula, there's like 1 that can use it for 4. Okay? We don't want to do that. Okay? We don't want to rely on a tool that isn't reliable. Okay? That's like saying, I can fix any problem with this single wrench. No, you can't. Okay? Everyone with me there? This is me saying, someone gave you this crutch because you weren't good at walking. I'm now going to kick that crutch out from under you and teach you to walk. Okay? Because we have to. All right, so we are not ever going to use a triangle. We're going to use the 3 rules of algebra that we learned back in chemistry. Okay? The 3 rules of algebra are, if I want to move something, I do the opposite operation. Okay? What I do to one side, I do to the other. And the 3rd rule we haven't used yet. Okay? Move what's not attached to what you're looking for first. And I'll show that a little bit more here in a minute. All right, right now, this formula is set up to solve for V. I would just plug in my numbers, do the operation, and have my answer. What if I wanted to solve for D? How do I isolate D? On the right track, yes. The final thing you said is right. I would change it to multiplication. I want to leave d over here because it's on the top. I can solve for it on the top. But what I'll end up doing is multiplying both sides by t, right? Because previously I was dividing by t. If I want to move t, I do the opposite. The opposite is multiply. And then I multiply both sides by t. That's essentially what I've done here. Okay? Essentially, I've said, okay, I'm dividing by t. The opposite is multiply. T cancels. What I do to one side, I do to the other. T times v equals d. Okay, that's the easy manipulation. You did that same manipulation with the mole equation, okay, when you were looking for mass and you had n and big M. That's the same operation you did. Now, here's where it gets different. What if I want to solve for t? Okay, our instinct here is, okay, I gotta leave t where it is, and I gotta move everything else. Okay, here's the problem. If I move d, I would have to divide, agreed? Because it's on the top right now, so I want to divide to get it over to the other side. If I do that, if I divide both sides by d, what's d divided by d? 1. So I don't cancel d. I leave a 1 on the top. Is 1 over t the same as t? It's not, okay? 1 over t is like 1 over 2. It's not the same as 2. Agreed? Okay, so what I would actually want to do instead seems like counterintuitive, but because t is on the bottom, I can't solve for it there. I need it to be on the top so that I can solve for it. So what I'm actually going to do, again counterintuitively here, is I'm going to move t over to this side. I'm going to move t, the thing I'm looking for. Now how do I get t by itself? Divide both sides by v. Right? T is going to equal d over v. That's the trickiest manipulation of that formula, guys. Okay? Was that terribly difficult? You can also always double check to see if you've done it right by plugging in the units. Okay? Typically, time would be measured in seconds. Typically, distance would be measured in meters, and typically v would be measured in meters per second. So if I divide meters by meters per second, what am I going to be left with? Seconds. Okay, well that means I did the manipulation correct. Okay, so that's a way you can check it. You can always plug in your units and see if you get the right units. All right. So we're not going to use triangles, we're going to use algebra, okay? And we're going to remember these 3 rules. And we're going to write them down again. Okay, so have you write those down, and then we're going to go over a couple of examples where we actually have to use all 3 rules. Okay? And those examples are going to be formulas we are going to use like next week. Okay? So I'm going to demonstrate to you why the triangle must go now. Well, let's say we're dealing with a formula that looks like this. Okay, this formula calculates acceleration. We'll be using it, like I say, probably next week. Right? So the A stands for acceleration. VF stands for final velocity. VI stands for initial velocity, and T stands for time. Okay? Now I can't use a triangle. Triangles don't handle subtraction and addition operations. This has got a subtraction operation in it, so I've got to do true algebra here. So let's do the simplest manipulation here. I want to solve for t. What should I do? can I solve for something if it's on the bottom of an equation? I can't. I would be solving for 1 over that number. That's not what I want. So I need to move t so that it's on the top. Easiest way to do that, since I'm dividing by t right now, would be to multiply both sides by t. All right, so I'm going to multiply both sides by t. Okay, so I've just done rule number 1 and rule number 2. Okay, if I want to move something, I do the opposite. What I do to one side, I do to the other. I've done that. Right? Now I want t by itself, so what do I have to do with a? Right? Divide by a. Right? Okay? All right, and what I did to one side, I did to the other. So now I've solved for t. That wasn't so bad. Okay? Well, let's set that up again, but now let's solve for something else. Let's solve for now instead this. So I've still got this formula. But now I want to solve for VF. Okay? This is where the third rule comes in. What do I move first if I'm looking to solve for VF? I should move what's not attached to VF. Okay? Is T attached to VF? It's not. There's no direct operation between VF and T right now. There is a direct operation between VF and VI. I'm subtracting VI from VF. That means that they are, in fact, attached. Okay? If I had two numbers right beside each other and I was multiplying them, they would be attached. Okay? But right now, T is separate, not attached to VF. Right? So it would be the first thing that I would move. And I would move it the same way we just did a minute ago. I would perform the opposite operation, and I would perform that operation on both sides. Now I've moved T. Now I'm left with VF minus VI, and I'm looking for VF. I've moved what's not attached. Now I have to move what's left. How do I move VI to the other side? What's the opposite of subtract? Add. Okay, so I'm going to add VI to both sides. Okay, negative VI and positive VI add up to 0. They cancel. Okay, and what I do to one side, I do to the other. VI plus T times A, or T times A plus VI, doesn't matter what order. Okay, and I've isolated VF. Did I have to use a triangle? Okay. Was there any calculus or really difficult, like nonlinear algebra in what we did there? All we did was follow the 3 rules of algebra. Guys, that's one of our trickiest formulas, to be perfectly honest. Okay, if you can manipulate that, you can manipulate anything that I'm going to throw at you. Right? As long as you follow those 3 rules, you can't go wrong. Okay, this is grade 8 algebra. I'm not going to ask you to do anything more involved than that. There's not going to be any trig in Science 10. Not that trig is all that hard either. Okay, it's just SOHCAHTOA. As long as you can remember that, you can do trig. All right, so let's have a look at a simple V equals D over T question. Let's have you write that one down and see if you can solve it. We're looking for how far a deer running at 15 meters per second would travel in 45 seconds. Let's look at this one. What should I do first anytime I'm answering a problem? Okay, write the formula, and to get the formula, because we're going to have a whole bunch of formulas now that we're in physics, I should write my givens, because they'll help me to figure out which formula I'm going to use. Okay? In this question, it wants to know how far a deer will run. How far is what? Distance. Okay, so in this question, I'm looking for distance. I know I'm not looking for displacement, or they'd ask how far and in what direction does it run. This just asks for how far. Okay? And it says it's running at 15 meters per second. What did they give me there? The speed. Yeah. Not the velocity, or they just said 15 meters per second north. Okay? Just 15 meters per second. And it does that in 45 seconds. Seconds usually measures time. Okay. All right, so you'd get a mark for that on a quiz or a test. Okay, writing out your givens is worth a mark. Because now, when you look at the back of your periodic table, there's a whole bunch of formulas there. At this point, I know I'm probably not using n equals little m over big M. Right? I don't have any of those givens, but I do have the givens for this formula. V equals d over t. And I'd get a mark for that. Okay? Because like I said, by the end of this unit, you're going to have 15 formulas to choose from. Okay? So you get a mark for figuring out which one you need to use. Do I need to do any algebra here? I do. I've got to solve for d. So I need to get d by itself by moving t. All right, so I'm going to multiply both sides by t, and I'm going to end up with t times b equals d. All right, you get a mark for your algebra. All right, then we're going to plug in our numbers. That's going to be 45 seconds times 15 meters per second. Okay, when I multiply those two things together, are my seconds going to cancel? Okay, I'll have meters seconds over seconds. The seconds should cancel, and I'd be left with meters. Okay, as my final units. That's good because I'm solving for distance, which is usually measured in meters. Okay, so 45 times 15, 475? Is that right? 675. 675. Okay, 675 meters. I don't put a direction on that because it's distance. Okay, and I'm done. That's the final answer to that. That's about as easy as they get. There's no long story to read in the question. Okay, the givens are fairly obvious, and it's one step for solving. Okay, they get more complex than that. We got some questions we'll do today that involve a forward and a backward, and there's a two parts to the question. What doesn't change is the math. All we're ever going to do is manipulate this formula. Okay? We might have to do it more times in a question, but that's all we're ever going to do. Okay? All right, questions on that first one? Okay. All right, try this one then. How long will it take a tortoise to crawl 200 meters at a speed of 0.25 meters per second? So in this one here, how long will it take? What am I looking for? Time. Yeah, time is always how long something takes. 200 meters. What did they give me? Distance. Okay, and I know it's not displacement because they didn't say what direction that 200 meters was. And they gave me speed because they outright say, here's the speed. Okay, 0.25 meters per second. All right, I'm looking for t. I have speed and distance. How do I get t by itself? Move t, right. I can't solve for something if it's on the bottom of an equation. I'll be solving for 1 over that number. So first thing I want to do, multiply both sides by t. Comes over here because I do the same thing to both sides. And then since I'm multiplying by v, to move it I do the opposite. It ends up over here. T equals d divided by v, distance divided by speed. Now if I plug my numbers in, I'll have 200 meters divided by 0.25 meters per second. The meters are going to cancel. I'm going to be left with seconds, and I'm going to be left with 800 of them, in fact. Okay, 800 seconds is what, like 15, 17 minutes, something like that. Okay. Is that a long time? Take a pretty long time for a tortoise to flop its way along 200 meters. Okay. All right, questions on that one? Okay. All right, so this one here is a vector one. Okay, so we're going to have changes in direction. Now which way we're going is going to matter. So I'm going to have you write this one down. We're going to do it together as an example of a vector problem where we're asked to do some scalar stuff as well as some vector stuff, and direction is going to matter. When I put the spray bottle down on the ground and I walk forward and backward, this is doing a similar thing. Okay, we have a bus that's traveling north, and then after that, traveling south. And we're trying to look at the trip as a whole, right? We're looking for the average velocity, okay, of the bus over this whole trip. So anytime I get a question that has two parts, I have to treat the two parts separately, at least to start with, okay? Because I have to remember that this formula really means average velocity is the total displacement over the whole trip, divided by the time for the whole trip. Okay? So what I want to do is write down my givens for each part of the trip. In the first part, okay, it says that the bus travels 100 kilometers north. This time they gave me a displacement. Now, could that also be the distance traveled in part one if I just said 100 kilometers? Yeah, when we're talking about a straight line, displacement and distance have the same magnitude because we're not veering off, okay, or reversing. All right, so in part one, the displacement is what they gave me, is 100 kilometers north. Okay, and the other thing they give me for part one is the time, 1.2 hours. Do I have to put a north on that? No. Time is scalar. It doesn't matter whether I go north, south, east, or west, time will pass. Okay? That's all I know for part one. In part two, okay, the bus travels 62 kilometers south. Okay, and that takes 0.9 hours. Okay, so here's what I often do when I see that in a question the direction is changing. Okay, what I'll do is I'll say, okay, north is positive, south is negative. Okay? And I'm just going to assign positive and negative to those opposite directions. Okay? If I had up and down, I would assign positive to up and negative to down. You pick whatever you want it to be. Okay, so if I'm going to calculate the average velocity, I need to know the total displacement and the total time. Can I do the total time right now? What do I have to do with 1.2 and 0.9? Just add it. It's scalar. Time is scalar. It just passes. Okay? So if I'm looking at another column here that says totals, okay, I know that my total time is 2.1 hours. Okay? That was probably the easiest calculation I would do here. Now for displacement. In this trip, essentially, what the bus does is this. It goes 100 kilometers north. And then turns around and goes 62 kilometers south. Everybody okay with that? Okay. I tell people all the time, draw a picture of the trip, visualize it. It often helps. Okay. So what that means is, this was my starting position, my initial position, and this is my final position. Displacement is your change in position. So would this gap represent my displacement? It would. So if I went 100 kilometers north and then came back 62, can I calculate how big this gap is? Okay, and what I would do, okay, if we want to calculate a total, what are we generally doing with all the numbers? Adding. Okay, but one of these is north and the other is south. That's why I assigned negative to south. When I calculate my total displacement, I'm going to go 100 kilometers north plus negative 32 kilometers. In fact, I won't even put the north in there. Sorry, not 32, 62. So plus negative 62. Is that the same as just subtracting 62? And if that works for you, go for it, okay? Mathematically, it's the same thing, all right? When I do that, I'm gonna end up with positive 38 kilometers, which, since positive is north, is 38 kilometers north. Okay, everybody all right with what I did there? I now have my displacement. I just calculated the gap between initial position and final position. So if I want to calculate the average velocity now, I'm going to take my total displacement, 38 kilometers north, and I'm going to divide it by 2.1 hours. Okay, and that's going to give me 18.1 kilometers per hour north. How important is it for me to remember to put a north on that? You'd get it wrong if you didn't. That's how important it is. Velocity is a vector quantity, so you got to have a vector on your velocity. Otherwise, it's something else. Okay, everyone follow what I did there? Okay, that's as tricky as they get. Okay, a two-part V equals D over T average velocity problem, that's as tricky as they get. Okay, now, I'm going to ask you another thing. What if instead of wanting the average velocity, the question also wanted the average speed? Could you calculate that? You could. And in fact, you would only change one tiny thing in the math we did. Everything else will be the same except one tiny little detail. What's the tiny little detail?
Displacement, distance, and just add them.
Right. Instead of adding negative 62, I just add 62. That's all that changes. I take this from being directions important, and this one's south and that one's north, to how far did I go? Don't care. Okay, which direction, just how far. So then I take 100 and add 62, and I got the distance. The time's still going to be 2.1 hours. Okay, then I divide the two, and I get the speed, which is going to be much greater, 77, I think it comes out to, okay, than the 18.1. Okay, because from a vector perspective, I only ended up 38 kilometers north of where I started. From a scalar perspective, I went 162 kilometers in the same amount of time. That means my speed is going to be a lot faster, even though it's the same trick. Okay? So, mathematically, are we doing anything super difficult here? We did V equals D over T, and we added and subtracted. Okay, I mean, that's not hard math, and that's how physics goes, guys. And I'm doing questions right now with my physics 20s. It takes us 10 minutes to do a question, and the only math we do is we multiply two numbers and then we add or subtract a couple of numbers. But it still takes us close to 10 minutes to do a question because we got to figure out what's going on in the question first to know what to do with those numbers. Which ones do I multiply? And then which ones do I add or subtract? Okay? Physics isn't about asking you to do math. Math is for its own sake. Okay? Math is a tool. Right? We use it in physics to solve questions when we figure out what's going on. The challenge is figuring out what's going on first. Okay, so I'm going to give you guys about a 5-minute break here, and then we'll try another question like this. Okay, 5-minute break within the classroom here, and then we'll try another one. All right, so this is a very similar question. Yeah. Okay, we have a rabbit who runs due east 22 meters per second for 12 seconds, then turns around and runs due west at 17 meters per second for 32 meters. Okay, we're looking for the average speed and the average velocity. Now this one does involve a little bit of other math that we didn't have to do in the last question, but it's not anything we haven't done. And it's just V equals D over T stuff. Okay, but what you are looking to do by the end, okay, is average speed is total distance over total time, okay, and average velocity is total displacement over total time. Okay, that's where we're headed. So in the end, this question wants me to solve for average speed and average velocity, which means I need to use these formulas eventually. Okay? What I want to do first is break this trip down into its two individual parts by writing down the givens for each part. Okay? First thing the rabbit does is run due east at 22 meters per second. So I know the velocity of the rabbit, 22 meters per second east, okay? And I know the time is 12 seconds. Okay? In part 2, I know that they turn around and run due west at 17 meters per second. All right, I've got opposite directions here, so I'm right away also going to do this. Okay? East is positive, west is negative, just so I remember that. Okay? And then this happens for 32 meters west. Okay, now they didn't tell me outright that the 32 meters was west, but they told me the rabbit was running at 17 meters per second west. It has to go west then. Okay, that's just one of those assumptions that I can safely make. All right, so if I want to calculate, first off, average speed, I need the total distance and the total time. And I don't have the displacement or distance for part 1, and I don't have the time for part 2, but can I find them? I can. I just have to use b equals d over t. So I got to do a couple of like intermediate calculations that I didn't have to do in the first one. Okay, so first thing I want to do is find the displacement for part 1. So if v equals d over t, I'm going to multiply both sides by t. Okay, so that's going to mean 12 times 22. Okay, so 264 meters east. Okay, there's the displacement for part 1. Now I know all 3 things for part 1. I'm going to do something similar in part 2 here. V equals d over t. So I'm going to multiply both sides by t and then divide both sides by v. Okay, so that's going to be 32 meters divided by 17 meters per second. The meters are going to cancel, and I'll be left with like 1.88 seconds. Okay, now I know displacement and time for all parts. Can I find the totals? Absolutely I can. Okay, so for the first part, wanting to calculate average speed, okay, I need total distance divided by total time. Well, distance, 32 meters and 264 meters. Because I don't care which direction for distance. Distance is how far I go. Everybody okay with that? All right, so to get the total distance, I just go 264 plus 32, and then for time, I go 12 plus 1.88. Okay, that's going to get me total distance and total time. So I'll have on the top 296 meters divided by 13.88 seconds. Okay, average speed of the rabbit is pretty close to the velocity in the first part. Okay, in the first part it was 22 meters per second. The average is 21. That's because in the second part, like he ran at 22 for 12 seconds. He only ran at 17 for less than 2 seconds. So that heavily weights the average speed in the favor of the first one. Does everyone follow? Okay. So 21.3 meters per second. All right, I've got the average speed. Now I want to calculate the average velocity. I do one thing different. Okay. Average velocity is total displacement divided by total time. 264 What's different? Right, I gotta make the 32 negative now. The 264 was east, the 32 was west. Okay, I didn't do that up here because I was dealing with a scalar quantity. Now that I'm dealing with a vector quantity, I'm going to add negative 32 or just subtract 32. I'm still going to have 13.88 seconds. It's the same trip, that part doesn't change. Okay, and now I end up with 232 divided by 13.88. Meters east, yeah, divided by 13.88 seconds. Okay, so the velocity is 16.7 meters per second east. How important is the east? If you want to mark for your final answer, it's important. If you don't have that on there, then it's speed and it's not velocity, and you didn't give me what I asked for and it's wrong. Okay, so on a vector quantity, you definitely need to include the direction. Okay, everybody all right with how that one worked? Okay, so you had to do a couple of extra V equals D over T calculations. That's going to happen, okay? But in the end, you didn't have to do any rocket science. Okay. Okay, I want you to write this one down and give it a try. It's easy in terms of it's one step. It's not a two-part question. But there is one little trick in it that we need to be aware of, and it's why we want to do this one. Okay, so in case you can't read my terrible writing, how long will it take a jet traveling at 330 meters per second? Sorry, that got cut off. Meters per second. Okay, to travel 400 kilometers. Okay, so I want you to write that one down and give it a try. When I write down my givens for this one, I'm looking for how long this is going to take. So I'm looking for time. Okay, they tell me the speed because they don't give me a direction on the 330 meters per second, which incidentally is very fast. Okay, this is basically the speed of sound, right? So this aircraft is almost supersonic. Okay, very, very quick. And it's traveling 400 kilometers. Okay, to find time, I would manipulate V equals D over T for T. So I'd end up with this, T equals D over V. But what problem do I have when I put in this? Right, yeah. The measurements for distance are different, okay? Distance is kilometers, but in speed, it's meters. Can I divide kilometers by meters? That's like dividing apples by oranges. They're not the same thing. I have to make my units match in any type of operation. Okay, so I can't divide hours, can't have hours in one and seconds in another. They have to be in the same units. All right, now here's the good news. Metric conversions are easy, but at this point, I expect that you have memorized the metric system. Okay, if you haven't, you need to. Here's the good news. It's going to take you no time at all because the metric system is brilliantly designed. How many meters in a kilometer? This is what you need to know. Automatic. Kilo always means how many? 1,000. Kilograms, kilometers, kiloliters, kilobytes. The metric system doesn't care what the units are. Kilo is always 1,000 times the base. Okay? Centi is always 100 of the base. That's why there's 100 centimeters in a meter. Okay? Milli always means 1,000. That's why there's 1,000 milliliters in a liter. Okay? So the metric system always uses the same prefixes, and it doesn't matter what the base units are. Grams, liters, meters, doesn't matter. They're all treated the same, which is brilliant, because in the imperial system, you had to memorize all kinds of stupid numbers. Okay? take it from me, because I actually lived in a time where we still used that, okay? You have to remember that there are 12 inches in a foot, 3 feet in a yard, 5,280 feet in a mile, and that there are 8 ounces in a pound, and, God, it's awful, okay? You have to remember, and there's this many fluid ounces in a cup, and this many pints, or cups in a pint, and this many pints in a gallon, and, okay, it's stupid, right? Having to remember all those numbers. The metric system, you just have to remember that kilo is 1,000 times the base. Okay, deca is 10 times the base. Hecta is 100 times the base. If you remember that, you can do any conversions you need to do in the metric system. That's why it was designed. Okay, it is so much easier to use. So, I just have to convert the kilometers into meters so that they match the meters per second down here. 400 kilometers is 400,000 meters, because there's 1,000 meters in a kilometer. So I just multiply that by 1,000 and I've got my meters. Okay, so like I said, at this point, I expect that you can do metric conversions like that. Okay, by the time you get to grade 10, that's automatic, or it should be. Okay, so in the end, what I have here is 400,000 meters divided by 330 meters per second. All right, so 400,000 divided by 330. Okay, so that takes 1,212.1 seconds. That's like just over 20 minutes. Okay, 20 minutes to go 400 kilometers. Okay, is that fast? That's super fast. Okay, 330 meters per second, that's fast. Okay, all right. So we would get 1,212.1 seconds, okay, for our time. And we leave it like that. Okay, you don't have to convert it to minutes or hours, it doesn't matter. Okay, unless they say how many hours does it take, then you convert it out. Right? Okay, questions on the metric part of this? Okay, guys, once you get using that, and you're going to a lot in this course, it'll just fall into place for you. But, okay, I did include in Google Classroom this handout here that can help you with that. Okay, it shows all the prefixes and how many times the base they are. Right? Really, we rarely go outside the main 6. Okay, so that's milli, centi, and deci. Okay, then you have the unit, and then you have deca, hecta, and kilo. We rarely go outside of those. Okay, down to 1,000, up to 1,000. Okay, we don't usually go outside of that into like mega and giga and yeah. All right. Okay, let's have you guys try this one to kind of finish off. It's much like the rabbit question, but it's an elevator. Okay, it's up and down instead of east and west. Okay, the answers are there in the squares, so you'll know if you did it right, because I don't know if we'll get time to go through it or not. Okay.